Yeah, last talk and 13th as well, so it doesn't bode well. The thing that really frustrates me is I never know which of these screens to look at. Nearly 3 minutes. Hi, I'm Steve Brown and I work at the University of Exeter in a group that try to look at engineering biofuels. And we've had some recent success with this paper in 2013 about heterologous expression of genes in E. coli that allow the production of alkanes. And these are good because they're replica fuel molecules to what we already have. So this is the group that I work in, and today I'm going to talk about a couple of methods that we're starting to employ, and I hope you can see some applications for your own work as well. The first one is using this dominant counter-selectable marker, Yeast, for gene deletion. This is my work with Solis and Escalante. And what it is you have a deletion cassette. Number one is 50 base pairs, 55 base pairs that are homologous to your gene of interest that you want to knock out. And this cassette in here, the ABCin, is a codon-optimized acetabidase gene from Aspergillus nigulans. It's also got terminate and things like that. What it does is, if this can be heterologously expressed in my strain, Saccharomyces cerevisiae, and it breaks down acetamide into acetate and ammonia. And ammonia is a utilisable nitrogen source. And when you grow, when you only have acetamide in the media as the only nitrogen source, then it can utilise that, and that's your selection. So you do this homologous recombination. It goes in with a selection of acetamide on the plates. And the other bit I should point out is this this 40 base pair sequence, which is homologous to just upstream of the region that's homologous to the I've lost my thing, but you can see they're both the same there. And what happens is you grow it in YPD, and this promotes homologous recombination, and you get this sort of rearrangement event. And what this does is allows you to counter-select on fluoroacetamide, which is toxic to the cells, so they still have this deletion cassette in. And what it does is it allows complete scarless removal of your gene and your marker. And this means you can use it over and over again, which is really positive. And it has, some advantages like the Krelox system. You have to do a second transformation, you get slightly poorly phenotypes. Just culturing in this way makes it a bit easier. And here's some success gel. This is the wild type of an ADH2 gene that I wanted to knock out. This is the insertion of the ADC cassette, and this lane here shows the deletion of it. The second methodology I'd like to talk to you about is an approach called design of experimentation. Now this is used largely by chemical and process engineers to optimise and screen experimental parameters. And what it does, it facilitates to design experiments, and this is really links towards like a synthetic biology approach and high throughput screening. So it really allows you to design your experiments and get the most amount of relevant information as you possibly can in the shortest time. It allows a dynamic evaluation of a multiple parameter interaction. So if we just go on to this part here, what happens normally, typically is you have one factor and one output, what you're measuring. For this case, it's biofuel production. And as you see, as we increase glucose, we find process optimum here. But things are very rarely one factor, and if we take into account a second axis, and this might be pH for instance, we'd keep this glucose concentration because that's where we think our optimum lies, and we would vary the pH around that. And what we find is our new biofuel titer improved is up here. However, the nice thing about DOE, it allows you to dynamically review these interactions, so the interaction in this case of glucose and pH. And if you were to run a DOE approach here, you'd actually find the process optimum would be in this design space, so somewhere that we've not even checked as yet. So allowing this, the structured experiment design lets you design these parameters, high and low values, and really to explore this entire space. A statistically relevant trade-off analysis is also important because you can look at the effects of, in this case, glucose and pH, not only for biofuel production but for increased glycolytic flux or a precursor or a product of interest, for instance.
Steve, 1 minute.
So what I'm trying to do with it, Saccharomyces is good, trying to use industrial manufactured products. Direct carbon flux predominantly through to ethanol production, this is bad. So I'm trying to use the AMD sync-cassette to knock out different ADH genes, and there are 6 involved in this step here. And directed modification of ethanol metabolism leads to very poor growth. So this is the trade-off analysis I'm talking about. So you can knock out all 6 of these genes, however, the strain is very poorly. So we propose that there's some combination of these gene knockouts that would let the strain have high glycolytic flux and also reduce ethanol production, because carbon is our currency, and it would be pterodactyl if that didn't use it. So this is just the orthogonal array showing you all the permutations. The green pluses are the wild type all the way through to the mutant. So yeah, there's lots of different combinations. It lets you review these combinations in different environmental impacts on these interactions as well. Thank you to Steve Ames, my supervisor. Everybody else, thank you for the Singer Foundation for sorting this out to be a nice opportunity. And I'll leave it on that. I'm very excited.
Awesome.